all of the parameterizations we've done so far have been parameterizing a curve using one parameter. What we're going to start doing in this video is parameterizing a surface in 3 dimensions using 2 parameters. And we'll start with an example of a torus. A torus, or more commonly known as a donut shape. A donut shape, and we know what a donut looks like. Let me draw it in a suitable, well, I don't have any suitable donut colors, so I'll just use green. So a donut looks something like this. So it has a hole in the center, and maybe the other side of the donut looks something like that. We could shade it in like that, and maybe it's shaded in like that. That is what a donut looks like. So how do we construct that using 2 parameters? So what we want to do is you can just visualize that a donut, if we were to draw some axes here, so that's our donut. Let me draw some axes. So let's say I have the z-axis that goes straight up and down. So the way I've drawn it here, the donut's a little at a tilt. So the z-axis, I'll tilt it a little bit. So our z-axis goes straight through the center of the donut. So that right there. This is going to be an exercise in drawing more than anything else. So that is my z-axis, and then you can imagine the z-axis goes from there, and then this on the coming out of here will be my x-axis. That right there is my x-axis, and then maybe my y-axis. Maybe my y-axis comes out like that. And the whole reason why I drew it this way is that if you imagine the cross-section of this donut, I'll draw it a little bit neater, but the cross-section of this donut in the x-z axis is going to look something like this. If I were to just slice it in the x-z axis, it would look something like that. I'm slicing, this is the x-z axis, right? That would be the slice. It would trace out, and we're thinking about not a full donut, just the surface of a donut. So it would trace out a circle like this. If you were to cut the donut in the positive zy axis, it's going to trace out a circle that looks something, like that right there. And if you go out here, you're going to get circles. It's just a bunch of circles. So if you think about it, it's a bunch of circles rotated around the z-axis. If you think of it that way, it'll give us some good intuition for the best way to parameterize this thing. So let's do it that way. So let's start off with just the zy axis. I'll draw it a little bit neater than I've done here. So that is the z-axis, and that is y, just like that. And let's say that the center of these circles, let's say it lies on, it can lie when you cross the zy axis. The center sits on the y axis. I didn't draw it that neatly here, but I think you can visualize. So it sits right there on the y axis, and let's say that it is a distance b away from the center of the torus, or from the z-axis. It's a distance of b. It's always going to be a distance of b, right? It's always, if you imagine the top of the donut. Let me draw the top of the donut. If you're looking down on a donut, so let me draw a donut right here. So if you're looking down on a donut, it just looks something like that. The z-axis is just going to be popping straight out. The x-axis would come down like this, and then the y-axis would go to the right like that. So you can imagine I'm just flying above this. I'm sitting on the z-axis looking down at the donut. It'll look just like this. And if you imagine the cross section, this circle right here will look just like that. This circle right here, that part of the top part of the circle, if you're looking down, would look just like that. And this distance b is the distance from the z-axis to the center of each of these circles. So this distance, let me draw it in the same color, from the center to the center of these circles, that is going to be b. And it's just going to keep going to the center of the circles. b. That's going to be b. That's going to be b. That's going to be b. From the center of our torus to the center of our circle that defines this torus is a distance of b. So this distance right here, that distance right there is b. And from b, we can imagine we have a radius of length a. So these circles have radius of length a. So this distance right here is a. This distance right here is a. This distance right there is a. That distance right there is a. If I were to look at these circles have radius a. And what we're going to do is have 2 parameters. One is the angle that this radius makes with the xz plane. So you can imagine the x-axis coming out. Do that in the same color. You can imagine the x-axis coming out here. So this is the xz plane. So one parameter is going to be the angle with our between our radius and the xz plane. We're going to call that angle, or that parameter, we're going to call that s. And so as s goes between 0 and 2 pi, as s goes between 0 and 2 pi, when it's 0, it's just going to be, you're going to be at this point right here, and then as it goes to 2 pi, you're going to trace out a circle that looks just like that. Now, we only have one parameter. What we want to do is then spin this circle around. What I just drew is just that circle right there. What we want to do is spin the entire circle around. So let's define another parameter. Let's define another parameter. We'll call this one t, and I'll take the top view again. This one's getting a little bit messy. Let me draw another top view. As you can see, this is all about visualization. So let's say this is my x-axis. That is my y-axis. And we said we started here on the zy plane. We are b away from the z-axis, so that distance is b. In this diagram, the z-axis is just popping out at us. It's popping out of the page. We're looking straight down. It's just like the same view is right there. And what I just drew, when s is equal to 0 radians, we're going to be out here. We're going to be exactly 1 radius further along the y-axis. Then we're going to rotate. As we rotate around, we're going to rotate and then come all the way over here. That's when we're right over there, and then come back down. So if you looked on the top of the circle, it's going to look like that. Now, to make the donut, we're going to have to rotate this whole setup around the z-axis. Remember, the z-axis is popping out. It's looking straight up at us. It's coming out of your video screen. Now, to rotate it, we're going to rotate this circle around the z-axis. And to do that, we'll define a parameter that tells us how much we have rotated it. So when we're over, so this is when we've rotated 0 radians. At some point, we're going to be over here. We're going to be over here, and we would have rotated it. This is b as well, and our circle is going to be looking like this. This is maybe this point on the circle, on our donut right there. At that point, we would have rotated it, let's say, t radians. So this parameter of how much have we rotated around the z-axis, how much have we gone around that way, we're going to call that t. And t is also going to vary between 0 and 2 pi. And I want to make this very clear. Let's actually draw kind of the domain that we're mapping from to our surface so that we understand this, I guess, fully. So let me draw some, and then we'll talk about how we can actually parameterize that into a position vector valued function. So right here, let's call that the t-axis. That's, remember, how much we're rotated around the z-axis right there. And let's call this down here our s-axis. And I think this will help things out a good bit. So when s is equal to 0, and we vary just t, so they're both going to vary between 0 and 2 pi. So this is right here is 0. This right here is 2 pi. We do some things in between. This is pi. This would be pi over 2, obviously. Pi over 2. This would be 3 pi over 4. We do the same thing on the t-axis. It's going to go up to 2 pi. Let's do that. So we're going to go up to 2 pi. 2 pi. I really want you to visualize this, because then the parameterization, I think, will be fairly straightforward. So that's 2 pi. This is pi. This is pi over 2. And then this is 3 pi over 4. So let's think about what it looks like if you just hold s constant at 0, and we just vary t between 0 and 2 pi. Let me do that in magenta right here. So we're holding s constant, and we're just varying the parameter 2 pi. So this, if you think about it, should just form a curve in 3 dimensions, not a surface, because we're only varying one parameter right here. So let's think about what this is. Remember, s is, let me draw it. Let me draw my axes. So that is my x-axis. That is my y-axis. And then this is my, getting messier, messier. That is my z-axis. Right. Actually, let me draw it a little bit bigger than that. I think it'll help all of our visualizations. All right. So this is my x-axis. That is my y-axis. And then my z-axis goes up like that. Z-axis. Now remember, when s is equal to 0, that means we haven't rotated around this circle at all. That means we're out here. We're going to be b away and then a away again, right? We haven't rotated around this at all. We're setting s is equal to 0. So essentially, we're going to be b away. So this is going to be a distance of b away. And then we're going to be another a away. The radius, the b is the center of the circle, and then we're going to be another a away. We're going to be right over there. So this is a plus b away. And then we're going to vary t. Remember, t was how much we've gone around the z-axis. These were top views over here. So this line right here in our st domain, we can say, when we map it or when we parameterize it, it'll correspond to the curve that's essentially the outer edge of our donut. If this is the top view of the donut, it will be the outer edge of our donut, just like that. So let me draw the outer edge. To do that a little bit better, let me draw the axes in both the positive and the negative domain. It might make my graph a little bit easier to visualize things. Positive and negative domain. This is negative z right there. So this line in our TS plane, I guess we could say, this magenta line, when we hold s at 0 radians and we increase t, this is t is 0. This is t is equal to 2 pi. That's t is equal to pi. This is t is equal to 3 pi over 2, all the way back to t is equal to 2 pi. This line corresponds to that line as we rotate, as we increase t and hold s at constant at 0. Now let's do another point. Let's say when s is at pi. Right? Remember, when s is at pi, we've gone exactly, pi is 180 degrees. When s is at pi, we've gone exactly 180 degrees around the circle, around each of these circles. So we're right over there. And now let's hold it constant at pi and then rotate it around to form our donut. So we're going to form the inside of our donut. So when s is at pi, and we're going to take t from 0. So when s is pi and t is 0, we're going to be, this was the center of our circle. We're going to be a below that. We're going to be right over there. And then as we vary, as we increase t, so as we move up along holding s at pi, and we increase t, we're going to trace out the inside of our donut. We're going to trace out the inside of our donut. That will look something like that. That was my best shot at drawing it. And then we can do that multiple times. When s is pi over 2, I want to do multiple different colors. When s is pi over 2, we've rotated up here, we've rotated exactly 90 degrees, right? Pi over 2 is 90 degrees. We're at this point. And then if we vary t, we're essentially tracing out the top of the donut, right? So let me make sure I draw it. So the cross section, the top of the donut, we're going to start off right over here. So when s is pi over 2 and you vary it right, and then you vary t, I'm having trouble drawing straight lines. When you vary t, it's going to look like this. That's the top of that circle right there. The top of this circle is going to be right there. Top of this circle is going to be right over there. Top of this circle is going to be right over there. So then I just connect the dots. It's going to look something like that. That is the top of our donut. If I was doing this top view, it would be the top of the donut just like that. And if I wanted to do the bottom of the donut, just to make the picture clear, if I make the bottom of the donut would be, let's see, if I take s is 3 pi over 4 and I vary t, that's the bottoms of our donuts. So let me draw the circle. So it's right there. The circle is right there. You wouldn't even be able to see the whole thing if this wasn't transparent. So you'd be tracing out the bottom of the donut, just like that. And I know that this graph is becoming a little confusing, but hopefully you get the idea. When s is 2 pi again, you're going to be back to the outside of the donut again. That's also going to be in purple. So that's what happens when we hold the s constant at certain values and vary the t. Now let's do the opposite. What happens if we hold t at 0 and we vary the s? So if we hold t at 0 and we vary the s, So t is 0. That means we haven't rotated at all yet. So we're in the zy plane. So t is 0. And s will start at 0. S will start at 0, and it'll go to 2 pi. It'll go to 2 pi. This is this point. Sorry, pi over 2. That's that point over there. Then it'll go to pi. This point is the same thing as that point. Then it'll go to 3 pi over 4. Go to 3 pi 4, and then it'll come back all the way to 2 pi. So this line corresponds to this circle right there. We could keep doing these. If we pick when s is pi over 2, or sorry, when t is pi over, do a different color. That's not different enough. When t is pi over 2, just like that, we would have rotated around the z-axis 90 degrees. So now we're over here. And now when we vary s, s will start off over here, and it'll go all the way around like that. So this line corresponds to that circle. You could keep doing it like this. When t is equal to pi, that means we've gone all the way around the circle like that. And now when we vary s from 0 to pi over 2, we're going to start all the way over here, and then we're going to vary all the way. We're going to go down and hit all those contours that we talked about before. And I'll do one more just to kind of make the scaffold clear. It's dark purple. Hopefully you can see it. When t is 3 pi over 4, we've rotated all the way. So we're on the xz plane. We're on the xz plane. And then when you vary s, s will start off over here. And as you increase s, you're going to go around the circle, just like that. And of course, when you get all the way back full circle, t over pi over 2, that's the same thing. You're back over here again. So this is going to be, we can even shade it the same color. And hopefully you're getting a sense now of the parameterization. I haven't done any math yet. I haven't actually showed you how to mathematically represent it as a vector value function. But hopefully you're getting a sense of what it means to parameterize by 2 parameters. And just to get an idea of what these areas on our ST plane correspond to onto this surface in our you could say in R3. This little square right here, let's see what it's bounded by. It's this little square. I want to make sure I pick a square that I can draw neatly. So this square right here, that it is between, when you look at t, it's between this, t is equal to 0 and pi over 2. So between 0 is t between 0 and pi over 2. And s is between 0 and pi over 2. So this right here is this part of our torus. This part of the torus. If you're looking at it from an outer edge, from the top, it would look like that right there. You can imagine we've transformed this square. I haven't even shown you how to do it mathematically yet, but we've transformed this square to this part of the donut. Now, I think we've done about as much as I can do on the visualization side. I'll stop this video here. In the next video, we're going to actually talk about how do we actually parameterize using these 2 parameters. Remember, s takes us around each of these circles, and then t takes us around the z-axis. And if you take all of the combinations of s and t, you're going to have every point along the surface of this torus or this donut. How do you actually go from an s and a t that goes from 0 to 2 pi in both cases and turn it into a position vectored, a 3-dimensional position vector valued function that would define this surface? We're going to do that in the next video.